바로 시작하면 되나요, 그러면? Hello, everyone. Good afternoon. This is Jeong-Gi from the School of Energy and Chemical Engineering at UNIST. And welcome to the international webinar on carbon neutrality hosted by UNIST Carbon Neutral Institute and the Office of the Public Relations. So today we have the distinguished speaker at EPFL, Professor Kevin Schuler. So personally, it is my great pleasure and honor to invite him and to share his recent achievement and to share his insight regarding the relevant field. So before starting his presentation, let me briefly introduce his research and academic background. So he received his PhD degree in chemical engineering in 2002 from the University of Minnesota in the United States. And he moved to California to get his PhD degree under the supervision of the Zhang Hreshet at UC Berkeley in 2007. And then he moved to Switzerland to pursue his postdoc research experience. And he then also worked as a group leader in the lab of the Professor Kratchow. And then in 2011, he was appointed as an assistant professor at EPFL, and he promoted to associate professor in 2018 actually. And he has been appointed as a senior editor of the ACS Energy Letters. So I guess that he might handle many papers regarding the electrocatalysis or photocatalysis. And he had a lot of publications and very prestigious awards. And let me briefly mention some of them. So he recently got Switzerland's Chemical Society Berliner Award prize actually in 2017. It is given to only one chemist every year, right? And under 40, as far as I know. And so far he has published about 150 papers. And recently he exploring the organic materials and polymer heterojunction material for solar energy conversion actually. And notably, he is also an advisor of our new faculty member, Professor Hani Cho. So I think this can explain you how he is great actually as a leading scientist in the solar field. So let's welcome Professor Kevin Sivula, and maybe you can share your slide now. Okay.
Yes, can you see my screen?
Yeah. So you are ready, yes. You can start your presentation.
Yes, I think I have shared the screen. Can you see
Yeah, I can see your share the screen. Yeah.
Yeah, it's okay.
Perfect. Yeah.
Okay. Well, let me begin also by thanking you, Professor Jeong-Gi, for the invitation. It's always a pleasure to have an opportunity to share some of the work that our lab has been doing on this topic of solar-driven water splitting. So let me get right into it. So the motivation behind this work is indeed for a future carbon neutral society. We will need ways to store renewable energy in the form of chemical fuels. And splitting water into its components of hydrogen and oxygen is a really promising avenue in this regard. We can imagine a future carbon neutral energy system relying on renewable hydrogen produced from renewable energy and processed together, for example, with carbon dioxide, performing reverse Fischer-Tropsch and water gas shift reaction to make renewable fuels, together with nitrogen to make ammonia and fertilizers for agriculture use, for all sorts of chemical and fuel-based applications. Well, the question is, how can we use our largest renewable energy source, and that of course is solar, and convert that into renewable hydrogen via water splitting? Of course, we can do this today using traditional photovoltaic cells and the dark electrolysis using an electrolyzer. where water will be oxidized on the anode and reduced on the cathode, effectively using sunlight to split the water into oxygen and hydrogen. But we don't do this today at any large scale. And the reason is because the cost for producing hydrogen is still significantly more than the state-of-the-art process for making hydrogen using the steam reforming of natural gas. Of course, that's a fossil fuel, but still the hydrogen is costing a lot more. Because of that, researchers like myself and probably some of you in the audience are quite interested to find alternative methods to convert sunlight into hydrogen via this water splitting method. And we can imagine doing this in other types of devices, for example, a photoelectrochemical or a photocatalytic particle-based heterogeneous system, where techno-economic analysis suggests that, well, depending on how we can make these devices, we might be able to produce hydrogen at lower cost compared to the photovoltaic plus electrolysis type of approach. In fact, this particle-based photocatalytic approach is quite exciting given the simplicity of this approach. We can imagine just making nano or microparticles of photocatalyst and dispersing them in water, and it's quite a scalable type of approach. However, this will require that we have a certain performance of our materials, of our systems, up to about 10% solar to hydrogen conversion efficiency. And that's where our work comes in, is to try to understand how we can engineer materials that would be used in these systems to increase the performance and the cost of the system. So while really our end motivation will someday to be using our materials in these particle-based photocatalytic systems, our lab mostly now focuses on these photoelectrochemical systems, because they both have something in common, which is that direct interface between the light-absorbing semiconductor material and the water that it's trying to react with. So I'm going to focus a little bit more on the understanding of this device here, with the idea that someday we're going to use it in this kind of system. So just focusing in on this photoelectrochemical approach, because the band gap of water at room temperature is essentially 1.23 volts, it makes sense to use both light-absorbing electrodes for the photoanode and the photocathode. So two semiconductor materials, both with their conduction band and a valence band, that can absorb complementary portions of the solar spectrum to increase the amount of light absorbed. And both of these semiconductors then will combine the photopotentials sufficient to overcome that 1.23 volts, which is necessary to split the water thermodynamically, and also the overpotentials for the water oxidation reaction on the photoanode and the water reduction reaction on the photocathode. Now, a key point here is the interaction between the semiconductor interface and the water, where ideally we would form this Schottky type junction that can help drive our photogenerated holes in the photoanode and our photogenerated electrons in the photocathode towards that interface, where they can react on a water reduction catalytic site on the photocathode or a water oxidation catalytic site on the photoanode. So this is the kind of the concept of the photo electrochemical approach, and then the analogous system with the photocatalytic particle-based system can be also imagined. Now, of course, our group is not the only group to be working on this. There are many demonstrations of many systems, and one of the highest efficiencies now is the system coming out of NREL in the United States, where Todd Deutsch and co-workers are applying these 3,5 type semiconductors like gallium indium arsenide, gallium phosphide in this kind of tandem cell and achieving very high efficiency solar to hydrogen conversion. However, the cost of these devices are prohibitively expensive. Indeed, something like this costs on the order of $10,000 for a small solar cell. So it's unlikely that this could ever be producing hydrogen at an economic cost. Another example of a material that's been quite successful for hydrogen production is this tungsten diselenide material. And here I'm showing for the first time an IV curve, which is something that we're going to show a lot in this talk. And this is a IV curve of a simple photocathode device made from a single crystal of this tungsten diselenide. And as the voltage is scanned here towards the more negative region versus the reversible hydrogen electrode, we see a photocurrent, and that photocurrent corresponds to the amount of hydrogen production that is occurring in this cell. And this material particularly has been quite successful and gives a very high photocurrent of about 25 milliamps per centimeter squared under standard conditions at the sort of open circuit potential, 0 volts versus RHE. But again, making single crystals of this material is prohibitively expensive. So that's really what motivates the work done in our group, where we'd like to be able to also think about performance, but also cost. So can we make high performance photoelectrodes that potentially could be scalable and cost on the order of only $100 per meter squared? And so to do that in our group, we think a lot about using widely available materials. And we think a lot about using solution-based processing techniques with the idea we'd like to have scalable roll-to-roll type production of these types of devices. But at the same time, we have to achieve high performance energy conversion. So we have to understand how these materials work and how to improve them. Our lab is interested in quite a few different types of material systems. For example, oxide semiconductors. They're especially interesting as a photoanode, which I will talk about very briefly later in my talk. Chalcogenide materials like this tungsten diselenide that I just mentioned, and the CIGS type material that's also being developed for thin films photovoltaic devices. And most recently, together with collaboration with now Professor Hanicho at UNIST, we've been working on developing organic semiconductors for this application of photoelectrochemical and photocatalytic water splitting. So today I'm going to try to tell you a little stories for some of these different materials, so you can get an idea of how we can try to engineer the material, increase their performance while trying to keep these inexpensive solution-based processing techniques. So let's get started with a very short warm-up story on this CIGS or CZTS-based semiconductor materials, which, like I said, are widely used in thin film photovoltaic devices and have the advantage that changing the composition can tune the band gap and energy position of these materials, so we can tune the driving force for the water reduction reaction here. We can also make nanoparticles of these materials by simple hot injection methods and coat them into electrodes. What we found to be very important is the need to anneal in a special way to reduce the grain boundaries in these electrodes and make the crystals grow from nanocrystals into microcrystals. So just to give you some electron microscope images to show you how we do this, here's a cross-section of a film showing here our nanoparticle CIGS layer before any annealing and without any of these special additives that help reduce the sintering temperature via a eutectic effect. But when we add this antimony, bismuth, or magnesium chloride, we see we can grow these crystals at relatively low temperatures and make large microcrystal particles that reduce grain boundaries, reduce recombination of the photogenerated carriers, and improve the photocurrent that we get out of the device. And to illustrate that here, again, I show some of these JV curves, or linear scanning voltammetry curves, where we change the potential and measure the photocurrent. In this case, we're turning the light on and off, so you can see the dark current and the photocurrent here. We want to get the largest photocurrent possible. And you can see in the non-treated sample, the black curve exhibits essentially no photocurrent at all. But when we use these additives to help increase the crystallite size, we do see a big increase in the photocurrent. And we can even make that better by applying some charge extraction layer, cadmium sulfide, titanium oxide as a protection layer, and using a platinum-based catalyst, we can increase the photocurrent even more, up to about 8 milliamps per centimeter squared, which is on the order of the same photocurrent that can be achieved using vapor-based depositions procedures with this type of material. Moreover, we see very stable production of hydrogen over many hours timescale with this type of photoelectrode. More recently, we've been quite interested in this system because we noted that even without any overlayers, without the cad sulfide, without the titanium dioxide, and even without the platinum, as shown in this black curve here, we can achieve, well, some promising photocurrent. And the idea of using this material in a photocatalyst and or in a very simple photoelectrode system without any overlayers, just directly using the material, is quite interesting, especially from an economic aspect. So our more recent studies has been focusing on understanding what's going on at the surface of this CIGS material. And we recently published this paper. I don't have time to go into all the details, but just very briefly, we found using electrochemical impedance spectroscopy, a large density of surface states which prevent the high photopotential and limit the onset of the photocurrent in this material. And using other techniques like in situ Raman spectroscopy, we've been able to help to identify these surface states and the active sites for the water reduction reaction directly on this CIGS surface. And overall, the conclusion is that the surface states are due to gallium and indium vacancies, but these are also the atoms that are participating in the hydrogen evolution reaction. So a future work should address avoiding the formation of these vacancies on the surface to improve the photopotential and the photocurrent on these bare CIGS photoelectrodes. So that work is ongoing in our lab. But that's just a small example of how we're trying to engineer one material like this CIGS material. I'd like to spend a little bit more time on a class of materials that we've also been developing in our group, and that's the transition metal dichalcogenide materials, indicated here by this crystal structure. They're quite promising materials for solar energy conversion in general because they're made of earth-abundant materials like molybdenum and sulfur, and they have band gaps that are relevant for solar energy conversion, high absorption coefficients, but more importantly for our application is they're known to be extremely stable materials. In fact, molybdenum sulfide is a material that's used for as a high temperature lubricant in many industrial applications. And that's because its crystal structure, like that of graphite, is this layered structure. So it can act like a lubricant. The layers can slide past each other, but its inorganic nature means that it can be stable at very high temperatures. But for photovoltaic applications, this material in the 1980s and 1990s actually gained a lot of attention and gave pretty good performance of devices, you know, just shy of 10% solar to electrical conversion. However, it was decided that the cost of these devices would be too high because the only way that they would work well is if we used, again, these single crystals. And it's quite difficult to make large area single crystals of these transition metal dichalcogenides. You can see here these pictures of single crystals, which can be purchased. They're only on that millimeter scale. And of course, for solar energy, we need large scale conversion. Nevertheless, more recently, Nate Lewis's group at Caltech, and I showed this graph already before, demonstrated that this tungsten diselenide can be an excellent material for hydrogen evolution, giving this photocurrent of 25 milliamps per centimeter square, compared to the only about 8 milliamps that we were getting in the best case with the CIGS. This material is performing a lot better. And I just want to point this out because it'll be important for later. This is another metric that we use in our lab to measure the performance or quantum efficiency of the photoelectrode as a function of the illumination wavelength. So different wavelengths of light have different performance. And what this says is that at 500 nanometer light, about 60% of the photons that are absorbed by the electrode are converted into hydrogen, right? So that's a pretty good performance for this single crystal photoelectrode. But still too expensive. We'd like to find a way to get similar performance, but using inexpensive solution-based processing techniques. Well, because of this material is a layered material like graphene, we can think about exfoliating it into single layer or few layer sheets using, for example, the Scotch tape method. These types of devices, either for photovoltaic or photoelectrochemical applications, have been developed in the past years and have shown really incredible performance, even with only a single atomic layer of these materials. But again, using a Scotch tape type exfoliation method on a single crystal leads to devices that are only microns in size. So very small active areas, which can be interesting for nano or microelectronics, but aren't interesting for solar energy conversion on a global scale. So we're quite interested to figure out if we could find a way to make these materials on a large scale. Well, John Coleman's group in Ireland a few years ago developed a solvent-assisted exfoliation method where a simple bulk powder of these TMDs can be added to a solvent like NMP and then ultrasonicated using a tip sonicator to basically exfoliate these in solution, giving us dispersions of these nanoparticles or nanoflakes that, well, look like this by transition metal microscopy. They're not perfect. We don't have single monolayers, and we don't have maybe nice shapes, but nevertheless, they're nicely dispersed. So we can think about trying to coat these on a large substrate to make photoelectrodes for our water splitting reaction. But a problem that we noticed when we tried to do this in our lab was we had very poor film formation. And that's because when we remove the solvent, the van der Waals forces between these basal planes of these flakes want the flakes to restack and aggregate. And just to illustrate that, here's an optical microscope image and SEM image of a drop cast film that we tried to make in our lab a few years ago. And you can see that these big aggregates of the material that we've made. So to overcome that, we had to develop a liquid-liquid based self-assembly method. And I just show you a video of how this works. But we can inject these flake dispersions at the interface between two non-solvents, and that confines the flakes at this interface where they reduce their energy. And we can load enough flakes here to fully make a film. And then we can simply remove the top solvent and then remove the bottom solvent through this vacuum filtration, depositing this self-assembled film onto the awaiting substrate below. Simply heat it briefly to evaporate the rest of the solvent, which we can use ethylene glycol or water, and we're left with this nice nanoparticle film on the substrate. We can do this on flexible substrates. We can do this over relatively large areas, which I'll show you later. But the most important thing is that our flakes have a good contact with our substrate. As shown here in this cross-sectional SEM image, our nanoflakes of our tungsten diselenide are all in good contact. Now, another problem here is all of these edge defects. These cause recombination, and initially these films didn't work very well for solar hydrogen production, but we found a way recently to overcome that. And let me just explain the reason why these edge defects are so problematic in these materials. The reason is based on the anisotropic charge transport in these nanoflakes. In fact, the charge transport in this direction parallel with the atomic layers is about 1,000 times faster than perpendicular out of the flake. So what that means is that a charge carrier generated some depth into a multi-flake film will much more fastly move towards the edge, and where these edge sites are atomic recombination zones, these charge carriers zoom quickly to kill themselves here at the edge, where what we want is them to move straight out of the surface. So one way to overcome that is to chemically passivate these edge sites, and we did that using this hexyl trichlorosilane chemical, which we can functionalize the selenium vacancies on the edges of this flake. And this has a positive effect on the photocurrent as shown here. In multi-flake photocathodes made and tested in 1 molar sulfuric acid with the platinum co-catalyst, we can see the effect of adding this HTS increases the photocurrent by about a factor of 3 or 4. So we're getting photocurrents here now on the order of about 4 milliamps per centimeter squared. That's a lot smaller than that 25 milliamps that the single crystal was giving. But we have to remember that our flakes are extremely thin, only a few atomic layers, and we're not absorbing a lot of light. So if we account for that by looking first at the quantum efficiency and the quantum efficiency normalized to the amount of light being absorbed, that's the absorbed photon to current efficiency here as a function of wavelength, we can see that closer to 600 or 700 nanometers, actually we're getting about 60%. That was the same as the single crystal. So despite the fact that we're processing these using solution-based processing techniques and making large area-based devices, we can still get quantum efficiencies that are similar. Moreover, we can show that the performance is quite stable for hydrogen production, and we can measure the hydrogen produced using a gas chromatograph and see that, yes, we have 100% Faradaic efficiency for the hydrogen evolution reaction. Now, since we've demonstrated this, we've done a lot more work in trying to understand the limitations of these nanoflake-based devices. One way to do that is to separate the flakes into different sizes and test these different size flakes that are produced by this ultrasonic method. And don't have time to go through all of the details, but here in this paper you can see. And what we found was that there was a nice link between the flake thickness and the flake width that really limits the performance of these ultrasonically produced devices. In fact, there is that correlation between the length and the width that we see when we do the ultrasonication means that we are never able to achieve flake sizes with a very wide width and a very thin thickness. And our calculations, our theoretical transport calculations, given this anisotropic transport in these materials, suggest that what we need to achieve are flakes that are very wide but very thin, and that will reduce the transport to these recombination sites at the edge. But we can't access that region using the ultrasonic-based exfoliation, and that's just due to the intrinsic material properties. So we have to find a different way to exfoliate these types of materials. Now, most recently, we looked at a new method called electrochemical pellet intercalation, where we take our bulk powder and make it into an electrode where we intercalate a large alkyl ammonium cation, which helps the exfoliation. It's a more gentle type exfoliation, which means that we can get much larger flakes with more pristine basal planes, as shown here, where we compare TEM images from the electrochemically intercalated flakes to the ultrasonicated flakes. And this new electrochemical intercalation approach means that we're able to achieve higher absorbed photon to current efficiencies compared to the ultrasonicated case. Now, I should note that in this data, this is a slightly different system, and we don't have any edge passivation on our flakes. But even without that, we're achieving this quantum efficiencies now approaching 90%. So even better than the single crystal in this case. So we're quite excited about this new method to produce these nanoflakes, and hopefully we can also show this for solar-driven hydrogen production in the future. But nevertheless, coming from a chemical engineering background, I really want to convince myself that we could do this on a scalable, on a global scale. So in fact, we did this recently just to show that this liquid-based self-assembly method, which is needed to make these films in good contact with the substrate, can be used on a roll-to-roll type device. And so we developed this in our lab just to demonstrate it. And I just show you some video here. Here's our liquid-liquid interface. Here's an injection of the dispersion. And we're pushing the self-assembled film with these Teflon-based paddles towards the substrate, which it's hard to see, but it's just coming up here. I can show that in another video just a little bit better. This is sped up about 4 times. We can see these paddles pushing that self-assembled film. Our plastic substrate is fed through, and it picks up the nanoparticle film, all in good alignment with the substrate. Now, this could be improved. Of course, the films that we make aren't perfect, but it's a good start to demonstrate that, at least in concept, this type of deposition could be scalable in a roll-to-roll sense. So up to now, I've been talking about these inorganic materials and talking about photoelectrodes. If we can figure out how to engineer these nanoparticles of tungsten diselenide or molybdenum sulfide, perhaps we can use them also in this heterogeneous particle-based photocatalytic system. And that's, like I said before, could be an ultimate goal to make hydrogen at the lowest cost. And there's a lot of people thinking about different materials for this approach. But there is one problem. And one problem with using inorganic nanoparticles or microparticles for this heterogeneous photocatalytic approach is that of charge separation. In a photoelectrode, the substrate and the work function of the substrate, together with the Schottky junction formed at the water interface, gives this driving force for charge separation. But in a standalone material like in this case bismuth vanadate or this tantalum oxynitride, there's not a heterojunction that can help really drive this charge carrier separation. And indeed, demonstrations of this inorganic photocatalytic approach have led to very poor solar to hydrogen conversion because of this poor charge separation. I want to note that there is a clever way that we can get charge separation in inorganic materials, and that was recently highlighted again by Professor Dolman in Japan, where he showed these single crystal strontium titanate materials. Because of their different crystal facets, which interact slightly differently with the water, absorbing slightly different species and generating a small difference of potential between the different facets, that potential difference can actually create electric field that can drive charge carriers separation and lead to charge separation in these nanoparticles or microparticles. However, a material like strontium titanate has a large band gap and doesn't absorb a lot of light. So work still needs to be done to figure out what kind of other systems this could be applied to. In contrast, there is a type of photovoltaic or material system that gives intrinsic charge separation on that nanometer length scale, and that's an organic bulk heterojunction. In fact, the material combination, for example, of soluble organic semiconductors like this PCBM and P3HT have been used in organic photovoltaics now for almost decades. And the interesting aspect of these materials is, in fact, upon light absorption, these materials do not produce free charge carriers. Their dielectric properties require this formation of a heterojunction between, for example, the electron donor and the electron acceptor, that upon light absorption, which creates a bound exciton, if that exciton is in high enough proximity to an electron acceptor, electron can be transferred from the donor to the acceptor, effectively separating the charges. And because these materials can be dissolved into the same solvent and cast out into the single film, this heterojunction can be formed really on that nanometer length scale. And this concept has been quite successful for photovoltaic devices, especially these solution process based, which are now in competition with the perovskite type cells. But what really interests me about this is the fact that potentially we can figure out how to use this concept in a bulk heterojunction photocatalyst. And we can imagine a nanoparticle photocatalyst like this that would have both donor and acceptor. And upon light absorption, we get that charge splitting on the nanometer scale to produce hydrogen in a hydrogen evolving photocatalyst and oxygen in an oxygen evolving photocatalyst. So that's really my dream. I want to note that recently, Ian McCullough's group at KAUST has shown some really promising results on just this hydrogen evolution type of a particle. However, there's some open questions about using organic semiconductors in this relatively harsh photoelectrochemical or photocatalytic type systems. Indeed, do we expect that these organic semiconductors could be stable for year-long application when they're in water and being shined on by the sunlight? This is a question that we were quite interested in. And I think we're justified in having that concern given previous work that's been performed on photocathodes using these organic semiconductors, where you can see the performance here. This is the photocurrent as a function of time under these light chopping conditions. And after only 1 hour, the photocurrent dropped by a factor of 2. That similar was observed in this EES paper in 2016, where they showed a similar type of drop in the photocurrent, despite initially having pretty high photocurrents here, up to 7 milliamps per centimeter squared. After only 1 hour, this dropped to below 3 milliamps per centimeter squared. Now, the authors in this case have attributed the drop in the performance to delamination of the platinums on the surface. And I think that is an important aspect that still needs to be addressed. But I think a more fundamental question is, can organic semiconductors, especially these bulk heterojunctions, be stable under these photocatalytic conditions or photoelectrochemical conditions? And that's a fundamental question that we wanted to answer in our group. So to do that, we took away the strict requirement of the photocathode to actually make hydrogen, and instead said, well, can we reduce something else that's a lot easier? For example, can we reduce europium-3 that's dissolved in water to europium-2? And we can imagine then this type of a system where we used a transparent electrode here with a molybdenum oxide layer to help align the work function. We used these PTB7TH and this PCBM C60, which should be able to reduce europium. And we note that the energy level of the europium is higher than that of the hydrogen reduction, so that if we can reduce europium thermodynamically, we should be able to reduce hydrogen as well. But this reaction should be a lot easier, just a simple 1 electron outer sphere reaction. So we can see that if we use a bulk heterojunction of these materials, we get pretty decent photocurrent here, about 3.5 milliamps per centimeter squared in these aqueous electrolyte with europium. But we see, similar to the other work, we see very poor stability performance. And after only 10 minutes, the electrode is essentially dead. However, we noted from some recent work in the photovoltaic field that these fullerene-based acceptors aren't so stable, and they cause a problem even in the photovoltaic application. So we thought maybe replacing that with a non-fullerene-based acceptor like this PDI-V could change the performance. And so when we made a new photocathode with these materials, we see, wow, we got a little bit better performance as a photocathode, but more importantly, we see a huge change in the stability. We see, in fact, a slight increase of the photocurrent over this 20 minutes, and that's probably due to the water which starts to ingress a little bit into this material, increasing the surface area. But nevertheless, a huge change in the stability in this sacrificial type system, which suggests that correctly choosing the molecular structure of these organic semiconductors is really important for getting stable photoelectrochemical performance. But nevertheless, we still wanted to test this system to see how stable it could be. We performed a lot of different tests at different light intensities, at different potentials, and using analysis techniques like electrochemical impedance spectroscopy and FTIR. And I don't have time to go into this, but the main conclusion is that we can still see a lack of stability in these systems if photo-generated electrons are accumulating at that bulk heterojunction electrolyte interface. That causes chemical damage if we accumulate too many charges. In fact, we can quantify how much charge we need to keep below on the surface to give stable operation. So what that suggests is that we need to coat the semiconductor with a really good hydrogen involving catalysts to extract the charges very quickly in order to achieve stable performance for a long time. And so we tried many different catalysts, and we found one, this ruthenium oxide. And I'm aware that ruthenium is not a very earth-abundant material, but it works quite well to demonstrate that if we choose the right catalyst, we can get high performance, up to 8 milliamps per centimeter squared, and pretty good stability, at least in this case, only losing about 33% of the performance over 1 day continuous operation. Now, we think some of this decrease is due to the catalyst sort of delaminating from the surface, as can be shown here with these SEM images. And after 20 hours, we can see these cracks formed and some of the bare surface of the electrode revealed, meaning that the catalyst is falling off. So again, linking the catalyst better with the organic electrode will be quite important. But nevertheless, these are solution process-based materials. We can make them over large scale, and we can show this sort of stable hydrogen evolution now for on the order of at least one day. But up to now, I've only mentioned 1/2 of this reaction, right? We're talking about the hydrogen evolution. In order to get overall water splitting, we also need the oxygen evolution. And to make sure that we absorb enough light, we want to use a photoanode that can absorb light, or an oxygen evolution particle that could eventually absorb light as well. So what kind of materials can we use for the photoanode? The most popular materials that have been developed are these oxide semiconductor materials. In fact, the first material ever shown was titanium oxide for overall water splitting. But again, the band gap of titanium dioxide is too large, so it only absorbs the UV light. Iron oxide and tungsten trioxide absorb more light given their smaller band gap. And in particular, this iron oxide material has been widely studied, also by our group, but is quite difficult to get to work well due to this poor electron and hole transport given this polaron formation. So more recently, investigators have looked at a wide variety of ternary-based oxides, including bismuth vanadate, which has a little bit too high band gap, but still works probably the best, and combinations of iron spinels or delaphoside type materials that have been looked at in our group. But I just want to give you one of the impression of one of the strategies that we have to use with these oxides to get them to function well. And so I'm going to take just a minute here to talk about this iron oxide. Iron oxide is a very promising material, or at least it's a very interesting material for solar energy conversion in general, because it's very cheap and abundant. And of course, it's environmentally benign. Iron oxide is essentially just rust. And this hematite form of iron oxide, you can see here in this crystal, actually absorbs a fair amount of the sunlight. Up to 16% of the standard solar spectrum can be absorbed. And the material is present everywhere on the surface of the Earth. So it's quite interesting material. However, it's got a lot of electronic problems. And just to summarize this, if we make a perfect single crystal hematite photoanode and we want to split water with it, producing oxygen, based on the amount of light that the crystalline hematite photoanode would observe, we would expect to see about 12.6 milliamps per centimeter squared photocurrent due to that oxygen evolution reaction. But we only observe about 0.5 milliamp per centimeter squared in these single crystal based electrodes. So one reason why that is because of the poor electronic conductivity in this hematite. We have to dope it to increase its conductivity. And as you probably know, we can dope a material adding an extra electron, but that changes this electrostatic interface between the semiconductor here and the water, specifically the Schottky junction that's formed and the width of the Schottky junction, because the width of the Schottky junction is proportional to the inverse square root of the number of dopants that we add. That can be okay in the material if the diffusion length of carriers is high in the material. But for the case of hematite, the situation looks really, really bad. We need about 400 nanometers of thickness of a film to absorb all of the light in hematite. But based on the amount of doping that we need and the diffusive transport properties, we only have light carrier harvesting from the first about 10 to 15 nanometers. What that means is that we need to nanostructure the material. And we spent a lot of time here at EPFL developing ways to nanostructure iron oxide. And here's one of the ways, using this atmospheric pressure chemical vapor deposition, that make these large area, high surface area nanostructures of iron oxide that can increase the performance. And we can see that here. The green curve is the photoanode LSV of a single crystal. And by increasing the surface area, by engineering the nanostructure, we can increase that photocurrent up to now about 3.5 milliamps per centimeter squared. But that's still a lot lower than the 12 that would represent a full quantum efficiency with this material. Now, many groups around the world, including in Korea, have looked at optimizing this material and have done very good, getting now about 6 milliamps per centimeter squared under the best conditions. But it's extremely difficult to engineer hematite more to get any more current out of it. It's a very challenging material. However, its stability under the water oxidation conditions is an advantage. And perhaps with further work, groups can find ways to further increase the photopotential and the photocurrent on this material. And I just want to end with a brief recent story. And I also have to acknowledge Professor Cho, who developed a very impressive strategy to use this bulk heterojunction concept actually as a photoanode to make water oxidation in our lab recently. He engineered, first of all, the right materials that can achieve the right energy levels for water oxidation in these organic semiconductors. And he had to engineer this interface here with the substrate to increase the surface area using a mesoporous zinc oxide, which helps to achieve a more stable performance. And by putting an overlayer here of this other PTAA organic material to help extract the charge carriers and reduce the accumulation of charges in the bulk heterojunction, along with a catalyst, a lithium-based iridium oxide catalyst for the oxygen evolution reaction, to achieve an impressive first demonstration of a photoanode using this bulk heterojunction concept with a photocurrent already of about 2 milliamps per centimeter squared. So not far off of even the hematite-based electrodes. The stability was improved with this PTAA layer, suggesting again that reducing the charge accumulation using a layer to extract the charges is important. And Faraday gas chromatograph measurements showed that oxygen was being produced at a Faradaic efficiency of 100%. So we are able to take then for the first time and combine our bulk heterojunction photocathode and our bulk heterojunction photoanode into an overall device that exhibited water splitting without any applied bias. So we just shine the light on it and we get spontaneous splitting and production of hydrogen and oxygen that we can measure with the GC. However, this first demonstration still had a relatively low solar to hydrogen conversion efficiency of only about 0.5%. So there's a lot of work that needs to be done on this sort of concept to get this to work at 10%, which we would need with also more than a year's stability to give it some reasonable commercial viability. But that means there's a lot more work for us to do in our lab. So I can see I want to leave a few minutes for some possible questions, but I want to give the take-home messages, which are that we can control the performance of these nanomaterials or solution processed materials by understanding defects in surface states, optimizing mechanical and electronic aspects of these materials to hopefully drastically improve the performance. And maybe someday we'll be able to make these over large scale electrodes and maybe make photocatalysts that can also work producing hydrogen in a very simple system at a cost that will be competitive with other approaches. So I have to thank funding shown here, thank my group for doing all of the excellent work. And well, thank you for your attention. I hope we have some time to discuss some of the aspects in this talk.
Thank you very much for your insightful talk. I was very impressed. It was very impressive to know that you are trying to do both fundamental and application studies at the same time. Very impressive. So for the audience, you can type your question in the Q&A window, or if you want ask a question verbally, you can click raise hand button icon, then I can allow you to speak in person. Okay. So first of all, there is some question actually.
Yeah, I see a question already here on the chat, and the first question on page 16, 17. Is there a specific reason why you use a liquid-liquid interface coding method? Yes. In fact, there is. This is quite important because if we've tried many different coding methods for these nanoflakes, and one that we thought might work would be sort of more the Langmuir-Blodgett or the liquid air-based interface. We can float our dispersions on top of a liquid, but as that solvent that the material is dispersed in, as it evaporates, it gives time for these flakes to aggregate. In fact, when we use the liquid-liquid interface, the liquid here that's in the dispersion goes quickly. It's soluble in both the top and the bottom layer, but the flakes are not dispersible in the top or the bottom layer. So it's really about that kinetics of getting that dispersion solvent away from the interface very quickly, away from the flakes very quickly. And that leaves the flakes to minimize their energy and stay at that surface, will not give them time to find a partner and aggregate. So we found that to be really important. And on page 39, I think there was another question there, and let me see if I can get there. The question is, how about to introduce some ETL materials on the polymer-based organic layer Yes, right. So this is something that we're actively looking into, both the ETL layer and a strategy to covalently link a catalyst to the ETL layer. Both of those strategies, I think, will be important for improving the performance of these photoelectrodes. So yes, this is a very important comment that we're working on.
So maybe as the audience needs some time to write the questions. So I have some simple questions. So I think the utilization of the organic bulk characterization structure is very important and to improve the efficiency of the photoelectrode.
Yeah.
Then do you think what is the most significant challenges to utilize them for practical applications at this point?
For which material specifically, the organics or?
Yeah, organic bulk character junction material.
Yeah. I think the most significant challenge will actually be one, it seems to be the stability. And there are a couple of aspects of stability that need to be addressed. The first is the actual link between the organic and the catalyst. So for both the water reduction and the water oxidation reactions, these are catalytics. These require catalytic cycles and close active sites. The polymer or the organic semiconductors themselves, as far as I'm concerned, they're not turning over the catalysis themselves. We're always going to have to add a separate catalytic site to drive the water reduction or water oxidation reaction. And that causes an issue because now there's a separate material that we need to get the charges to, and we need to make sure that that material, that catalytic site stays at that interface. So that's one challenge. And then another challenge is to understand the actual intrinsic stability of these materials. Under relatively harsh conditions with sunlight and with water around, can they be stable for a year is an open question. So we'll have to still look at that. And this is a harder question to answer because especially in the forum of our research lab, a PhD student is reluctant to study a system for 1 year to get the stability data on 1 year. But this is something that we'll have to do.
So thank you very much for your answer. And there's one more question from Professor Jihyun Chang in our department. So thank you for the nice presentation. Please briefly tell us how you can improve the stability of your organic semiconductors in the Nature Catalysis paper.
Yes, yeah, thank you for the question. And I'm sorry, this was getting to the end of my talk. I didn't have a lot of time. So there are two aspects of this, and I don't show the data for this in this talk just due to time. But we found something quite interesting, which was the short-term stability, especially of this photoanode, was directly related to the substrate that we put the photoelectrode, the bulk heterojunction layer on. If we used a flat substrate, there's very limited surface area in contact from the bulk heterojunction and the substrate. And we found that under the conditions that we used for testing, the water would sort of delaminate this organic layer from the organic layer. That led to very poor stability. But when Professor Cho decided to put the mesoporous zinc oxide. So this is a nanoparticle zinc oxide substrate with a very, very high surface area. And this gave more surface area for the bulk heterojunction to sort of adhere to. And that drastically improved the stability under this. First, we observed that under the sacrificial sulfate oxidation conditions. But that's also true when we built the entire system and improved and put the PTAA whole transporting layer on top, which is the second invention that Han He made to improve the performance. So using this whole transport layer helped to extract the charge carriers quickly so they don't accumulate in the bulk heterojunction. This is a big problem because the oxygen evolution reaction is kinetically very, very slow. And in other systems, especially the oxide photoelectrodes, the observation of a large amount of charge accumulation in the semiconductor itself is necessary to develop the photopotentials that can drive the OER reaction. We also need that in our bulk heterojunction system, but if we accumulate the charge carriers in the bulk heterojunction, then those charge carriers will probably just oxidize the organic itself, which we want to avoid. So we have to get those charge carriers out with this PTAA layer, whole transport layer, and then they feed them to the catalyst. So that was the second way we improved the stability in this photoanode. Yes.
Thank you for the answer. And actually, we have the Professor Chang-Dok Yang raised his hand to ask a question.
Okay, can you hear my voice?
Yes.
Okay, thank you. Thank you for nice presentation. And in this slide, and I just wondering, when you're making the bulk heterojunction and anode, photoanode, but you're applying the PTAA as a HTL, but just my view, and generally that is a inverted cell bulk heterojunction, but you can apply HTL as a molybdenum oxide generally. What is the role of the PTAA and organic HTL rather than inorganic molybdenum oxide?
Okay. That's an interesting comment. So right. So there are plenty of other HTLs that we could imagine using. So you're right. For the photocathode work, we used on the substrate an HTL of molybdenum oxide. So I think if I understood your question correctly, why don't we use something like the molybdenum oxide here as an HTL for our? Yes, this is something potentially possible. But another thing I didn't have time to explain is that the molybdenum oxide isn't stable at the pH that we would like to do the water oxidation reaction. So the molybdenum oxide, when we put it in water, it's only stable at very or acidic pHs over a short window. So actually, one thing that I didn't have time to mention was that for our photocathode in our tandem cell, we used the same pH of pH 9 in this system, and the molybdenum oxide actually isn't stable. So we had to use a self-assembled monolayer, an organic layer, a different type of whole transport layer here to get this to work well. And you can check out the paper that was published recently. But this is an important point. So one thing that we always have to think about is that we don't have to think about in the OPV field is, are the materials that we're using stable under the conditions that we have for testing? In this case, under pH 9, which is better for the OER, but more challenging for the hydrogen evolution reaction. Oh,
sorry for any inconvenience. And
no,
actually,
okay.
you can also check the question in the
There's a question: is there any advantage in photoelectrodes when using flexible substrates? I think it's a good question. There's an advantage when if using inexpensive substrates. In fact, the techno-economic analysis, which is similar to the thin film solar cells, one of the largest costs in making the PEC tandem cell would be the glass substrates, right? So reducing that, using inexpensive plastic substrates that are coated could reduce the cost of the PEC cell. But in principle, there's no real mechanical advantage. Han Hee has a question. Hello, Han Hee. Thanks for the talk. I have a simple question about bulk heterojunction photocatalysts. If you have a bilayer polymer system which has a comparable performance to a bulk heterojunction, do you still need a bulk heterojunction strategy to demonstrate polymer-based photocatalysts? No, bilayers will be fine. But in fact, this is one interesting approach to think about making bilayer on that length scale of sort of 20 nanometers of donor and 20 nanometers of acceptor, and then thinking about how to make a sheet of this. Maybe we could have a photocatalytic sheet that would work fine. So as long as we have the materials in close enough proximity so we can get, so what light absorption and exciton can diffuse to the interface between the donor and acceptor in the organics, then we don't need the bulk heterojunction. We just need some sort of heterojunction. And another question here, if I have time, is there any strategy to safely separate the oxygen, hydrogen? Wow, yes, this is another very important question. So separating the oxygen and the hydrogen is really important. In the photocatalytics kind of system, we can imagine a cell with a membrane that would already separate the hydrogen and oxygen. And the same thing with the photocatalytic system in what's called the dual bed based photocatalytic system. So I think that any future application will integrate this sort of dual bed or separate compartments for the oxygen and hydrogen evolution, so we don't have to worry about separating them afterwards. In fact, if we have both of them evolving on this system, there'll be a lot of the back reaction that's occurring, and we want to avoid that as well. But that's another complication for engineering this redox shuttle that would have to be used in the photocatalytic system. Lots of work to do, especially so if we can find systems that can do these reactions for low cost and at high efficiency, then that next level of engineering will come.
Okay, I think because of time limitation, we have to wrap up the webinar at this point. Actually, I heard that he also has a morning class, so we cannot have him forever.
I have to get teaching, yes.
Anyway, let's thank him again. And I also would like to appreciate the audience who actively participate in the webinar. Okay, thank you very much.
Thanks for all the questions. Thank you.
Yeah, thank you. Thank you very much. Okay.